So I'm going to give the floor to Andreas to start today's session.
1 second. Oh, okay. So thank you very much for the kind introduction. My talk will be divided into 2 parts mainly. So first I want to start with one part, how we can connect NMR data to MD simulations on the example of RNA. And the second part will mostly focus on how to get the structure of RNA tetraloops, describing them by NMR and by MD. So because I think most of you might not be that familiar with RNA, I wanted to start with a slight introduction of what we can actually measure for RNA using NMR. Obviously, the first parameter we can determine are the NOEs. They are great. They are the first starting point, or one of the most important starting points for most structure calculations. The only problem is that we have this limitation of 5.5 angstrom, and the nucleotide is actually quite large. So you can see here, for example, an intramolecular NOE in just guanosine is already at 3.8 angstrom. So 5.5 is really not a lot to work with. The other very important point are the aminoprotons that are involved in base pairing. I'm sure most of you know that in DNA, we are mostly having Watson-Crick type base pairs. In RNA, there are many, many more different base pairs. We have Wobble base pairs, we have Hookstein base pairs, we have sometimes even base triples, or in some cases, even tetrates that are forming base pairs. And these are one of the main structural features that we need to describe by NMR, or we are able to describe by NMR. So it's really important for us to know about these. The last point, I think you're also quite familiar with, dihedral angles. Compared to proteins, where I think you have only 2 backbone angles, in the RNA, we have a total of 6 backbone angles and 1 glycosidic torsion angle. And we can determine all of those 7 angles using J couplings and cross-correlated relaxation rates with 2D or either 3D experiments. So first, I want to start off a little bit by what's the problem with NOEs. And in most structure calculations that we do, the distance error on an NOE is mostly defined by plus minus 1 angstrom in a lot of cases. So you can imagine if you have these large errors, then the global fold of especially a very rod-like structure can change quite drastically depending on how large your error is. Another problem that we often see is we have averaging for RNA, and especially if you have some very small distance and some larger distance, you might not detect it on the cross peak correctly and cannot assess it directly. We can circumvent this or just use RDCs, similar to proteins as well. In our cases, we mostly use PF1 phages as an alignment media, and the great thing about RDCs is that they are very sensitive to the overall fold of your structure. So the proton is very sensitive to its angle compared to the alignment vector of the sample, and therefore we can really easily distinguish using RDCs between 3 different global folds, for example. So combining NOEs and RDCs is already great. Averaging cannot only happen in NOEs, but also in couplings. The example I give you here is for the pseudo-rotation phase of the sugar moiety. And mostly we have the C3' endo conformation that we mostly find in the stem regions. And often we have the C2' endo conformations for loops and bulges. So whenever we need to elongate the structure, this is one of the ways the RNA can do with this. And normally we would expect for both C3' endo and C2' endo that the 3JH couplings are in these blue regions up here. So they would just flip if we change from one conformation to the other. But now you see for these 2 examples I've brought here, where they're in neither of these regions. So we know just from measuring those couplings that we have an averaging of at least 2 conformations for these examples. And if we want to get the structure of an RNA, one thing we can do is connecting our NMR data to MD simulations to get the average ensemble structure. And we can either use restrained MD simulations, so we immediately take the NMR data, put it into the MD simulation, use it together with the force field, and then get an MD trajectory. The only problem with this is if you acquire new insights, you have to rerun the entire MD simulation because it was already predetermined by experimental data. The other option, which I will introduce today a little bit in more detail, is running an MD simulation, collecting a large number of frames, and then using our NMR data to reweight the structures that were sampled during the MD trajectory. And I'm mostly focusing on this maximum entropy, Bayesian maximum entropy approach. So the idea behind it is that in many cases, especially for RNA, the force fields that are available, they differ quite a bit for different RNAs. So depending on what force field you use, you might get very different results. And the idea is if we sample just enough space, we might not sample everything how it is in nature, but we will sample the populations that are relevant, at least to some degree. And by reweighting, we can shift the simulation average to resemble something more of the experimental average. So we don't change the MD simulation at all. We just change the weight of each frame in the MD simulation. One potential disadvantage when you do this is that you can lose time-dependent information because you're selecting single frames. And it can be quite dependent on the scientist that is doing this due to the choosing of the hyperparameter theta. What is this, you might ask? And these pictures these figures were nicely provided by David. He has been doing his master thesis under my supervision and is now doing his PhD. And basically what we see here, first, I want to point to you the phi effective. This is just the number of frames that are actually having substantial weights after the reweighting. So you see, if we change this line here, which is corresponding to this value theta, we decrease the amount of frames that have actually substantial weights. So you can now imagine if we use a very, very small theta, then we just use a couple of frames, while if we use a very large theta, we are using basically all the frames of the MD simulation. And one thing we have to keep in mind is we don't want to over-restrain our MD simulation. So to combat this, we not always use all the NMR data we have available, but we divide it into a training data set and a reference data set. The training data set is actually used for the reweighting, while the reference data set is just used to make sure that the MD simulation is not too focused on just fulfilling the parameters that we have used for the reference. And you can see here, for example, if we just use, I think these are the HCP, the gamma HCP rates and the relative change of the gamma HCP rate after reweighting, and the, I think, RDCs over here, we can actually get to a point where our HCN rates, they do not improve, but they actually decrease in the relative error that we have there. So we over-restrain some structures. So we really want to prevent this. Now you might ask, okay, how does it look like if we change different thetas? I think I skipped just straight to the slide. So in orange at the bottom, we have an unweighted simulation. So you see here, every frame of these 20,100 frames is exactly identical. So the weight is 1 over the number of frames. And if we choose, for example, a theta of 3, then we just choose very, very few frames to actually describe all of our NMR data. So we have a very narrow view on the MD ensemble. If we use a very high theta, then a lot of frames are getting low weights, so they are included in our description, but they're really not contributing that much. So we really want to choose the elbow point here, where we have a balance of frames that are actually having significant weights, so significant contributions to explain our experimental data, but we don't get too many frames that are basically not that relevant to describe our experimental data. Oops, sorry. Another thing you have to keep in mind if you're doing this approach is it really depends on what your training data for the reweighting is. So it can be quite different what data you use and how you combine different data sets. And I would advise everyone who's trying to do this to choose different combinations, because as you can see here, for example, if you just combine N-orith and 3-J couplings, actually doesn't look that great. So we see the elbow point is quite far up, so we need a lot of different structures of the MD simulation to explain or to improve the back calculation of of the simulation average to the experimental data. While if we use the gamma ACCH rates and the RDCs, we can explain our experimental data with fewer structures. And I think this is quite important because if you think about it, yes, you can explain every experimental data point if you have just enough structures, but this is not what we want to do. We want to get the structures that are actually relevant to describe our experimental data and not just any few. So with this, I want to conclude this part of the presentation. If you're curious and want to try this out, all the scripts are available in these GitHub links. These two are mainly focusing on RNA, but I think this one, if I remember correctly, has also plugins for the reweighting, also the Bayesian maximum entropy reweighting of proteins. In the second part of my talk, I want to focus on RNA tetraloops and how we can actually in detail describe their structure using NMR. I want to start with a brief introduction of tetraloops, because I'm sure not everyone is very familiar with those. The first or not the first, but one of the most important tetraloops is the UCG tetraloop. This was published many, many different times throughout the last, I think, 30 or 35 years. And even initially, there were quite a few very high resolution structures solved by X-ray and some by NMR, and they were already looking quite good. But as you can imagine, when a structure was published in 1999, the spectrometers improved, and also the experiments that were available for us improved quite drastically in the following 10 to 15 years. So what a PhD student from our group, Zenada, together with Boris Völtig did, is they, after every experiment was available, to measure all the parameters that I just showed you, so all the dihedral angles, all information about base pairs, RDCs, and so on. They used all of this information to calculate a new structure, and you can see here quite nicely that if you just use NOEs, you get a quite nice looking structure, but if you include the RDCs, if you include the dihedrals, if you include everything together, you get one very nicely converging high resolution structure where actually the RMSD of the loop is very, very good. And this structure was then in return used quite a number of times in different publications, for example, as a model or a reference model for MD simulations to figure out how good new force fields are. But what people noticed is that the UCG tetraloop is quite unique in that it is basically a molecular rock, and RNA force fields need to be able to describe more dynamic systems. And what you can also probably imagine is the tetraloop, so you have 4 nucleotides, so 4 over 4 possibilities to 256 possible combinations for tetraloops. And if you look into the PDB, and in nature, you find quite a few different tetraloops. One of the 2 main clusters are the GNRR-fold tetraloops and the UNCG tetraloops. UNCG is the overarching class for the UCG tetraloop, where N is describing every possible nucleotide, and GNRA is just any nucleotide on the second position, and an arginine or guanosine on the third position. And as you can see already here, there are quite a number of structures in the PDB for these classes of tetraloops, and they actually fill out a good space in the PCA analysis. Then there are U-turns, four-stack motifs, and it's going and going and going. So there's a quite large variety of different tetraloops that can be found in nature. But I will focus only on these 3 tetraloops throughout this talk to explain to you a little bit how we can actually describe RNA with NMR, because these tetraloops show a very much more dynamic behavior compared to UCG. So if you look at the UCG here, we have here the 1H carbon HSQCs of the sugar moiety. And you see throughout the temperature series, starting at 0 degree, going up to 35 degree, there's actually not much happening here in either of those 2 regions. If we go to the GAG or GCAA tetraloop, they are actually way more dynamic. So throughout the temperature series, we see a very, very large temperature response, indicating that these tetraloops, they must be way more dynamic than, for example, UUCG. And CUG is quite special because it's not the most common tetraloop, but it's quite unique in its structure, and it's very often very highly conserved. And therefore, we also decided to look at this. And when we analyze the temperature row, we see, yeah, we have some dynamic behavior over here, way more than UCG, but nothing compared to the GNRR tetraloops. But what we observe actually here is that the first and the last loop residue, they undergo intermediate exchange if at around 25 degrees. So we were wondering, okay, what is happening here? This is interesting. We also analyzed the sugar pucker using something similar to Talos predictions. So this is just a chemical shift-based approach to get an idea about the sugar pucker and the angle gamma. And you just, if you have the assignment of all the sugar, of the carbons of the sugar moiety, you can use just these two equations, and you have a very good idea if your RNA or if the sugar moiety of a given nucleotide is in the aforementioned C3' endo conformation or in the more unique C2' endo conformation. And this can also be displayed as a function of the temperature. And again, UCG, there's really not much happening here. So molecular rock, CUG, we see there are some temperature-dependent shifts. And what's quite interesting here is, for example, that we don't have a linear dependency, but there's a curve in this trend indicating that there are more than two states that are responsible to describe this behavior. And lastly, GCAA and GAG, you can see here again, their temperature response is quite significant, again, hinting to possible dynamics. Going back to this picture, this is everything or most of what we can determine for RNA. And I first want to focus on the on the assignment, because as you can imagine, there are quite a number of experiments that you can actually use to get a full assignment of any given RNA. I think it looks maybe at first a little bit overwhelming, but you don't need to measure everything. It's just a possibility of combinations that you can do, and you can actually combine most of these experiments quite nicely, I think. And I've also included some of the measurement times that we used for most of these experiments. Now, what you might think is, okay, so I need isotopically labeled RNA to measure all of these experiments because most of these are 2Ds or 3Ds, and that is quite expensive. Yes, it is expensive, but please keep in mind, compared to proteins, where sometimes I've heard colleagues complain that their proteins are degrading after 2 hours of measurement, these RNAs, you produce them quite quickly, so it takes at most 3 to 4 days if you've kind of established the production, and then they are stable for a year, 2 years, 3 years, 4 years. We have one sample actually in our lab that is, I think, 14 years old. So you can just keep measuring and measuring and measuring. So you don't have to think about having to reproduce these RNAs all the time. So I think it's quite worthwhile to produce isotopically labeled RNAs, especially if you're very interested in the system. What I want to point out is, I know this might look a little bit intimidating, but actually some of my colleagues have worked together with Bruker on a very nice tutorial that is now, I think it will be released soon in Biotop, where they've basically explained how to do the assignment of RNA from scratch with example spectra, with the experiments that you use, and they are all in Biotop. And I think the general settings of those experiments are already quite decent. And if you have some experience with NMR, you can improve these experiments quite a bit and get really, really nice spectra quite quickly. So if you have a project where you might need to describe the structure of an RNA and you're wondering how to start with it, I think this is a great, great tool. So next, I want to go to the hydrogen bonds or the base pairs, because as I've mentioned before, base pairs are very, very important in describing RNA structures. And if we go to the CUG tetraloop, well, we have a CUG base pair here, so there's a possibility of a Watson-Crick base pair forming that will definitely stabilize the loop by quite a bit. Now, the problem with iminoprotons is that while they are great and while they give us a lot of structural information, they really tend to like to exchange with solvent water. So you need a population of around 90% of the base pair being protected from exchange with water to be actually able to observe the proton. And this is mostly the case at lower temperatures because everything is a little bit slower at lower temperatures. So we are often, it's quite nice to actually observe most of these base pairs at low temperatures. But everything else, we really want to measure at high temperatures, so 35 degrees. And there I wasn't able to observe this base pair anymore. But I can't really, in good faith, restrain a base pair that is so important for the structure of an RNA if I don't see it at high temperatures. So I opted to use a different experiment because there are actually quite a few numbers of the experiments to probe into base pairs. And this just starts on a non-exchangeable proton and then does a transfer throughout the ring and then across this base pair and this bond. And with this, I was able to actually prove that this base pair is formed at higher temperatures, although if we assess the cross-peak intensity to a much lesser degree than every other base pair in the RNA. So we know there are at least two states, one where the base pair is formed and one where at least the iminoproton, which is sitting right in the middle of the base pair, is somehow accessible for solvent exchange. And this is really nicely in tune with our observation here that we have this intermediate exchange at 225 degrees, and then these peaks reappear in fast exchange at high temperatures. Now, you might say, okay, that's nice. That is a Watson-Crick base pair. It should work quite nicely. What about all the other base pairs that you've told me about? And actually, there are also experiments, for example, to probe into more interesting UU base pairs or GU base pairs. So you see in these two RNAs, there are actually quite a number of possible combinations for non-canonical base pairs. But as I said, you need a population of at least 90% to be protected from solvent exchange to be able to see them. We didn't see them. Not very surprisingly, to be honest. But there's a very cool experiment, which is a CN direct detected HSQC. And basically how this experiment works is we have 3 times during a transfer that we set to different values. So just one is 0, one is 1 over 2j, and one is 1 over 4j. And during this transfer, the water from the solvent can exchange with the proton, and this will lead to a sign change at the time point where we have 1 over 2j of the HN coupling. At the time point 0, every signal will be positive in this experiment, so we are able to see every single uridine or guanosine in this experiment, and we can then assess, if we use the second time point, does it drop to negative? Then we know it's protected from solvent exchange to some degree. If it disappears, we know there's some intermediate bond going on. And if it just stays positive and we see some decay, we know this is really accessible to solvent exchange. There's no protection whatsoever going on here. And with this experiment, we were actually able to prove that we do not form a base pair between these two U's in the loop here, for example, which we originally thought would be the very likely thing to form, because then we have a UU base pair here, a UG base pair here. This should be quite stable, but no, we actually have a UG base pair going diagonally over this loop. So this was a key finding for this structure. And we also found out that in this bulge here, yes, we have a UU base pair here, and we have one U that is slightly more protected from exchange with water. So our reasoning was, okay, maybe we have to some degree a UU base pair forming here and a UG base pair forming here, or even sometimes a base triple. I think this experiment is quite handy and can be really great to assess non-canonical base pairs if you have them in your structure. The next point I want to focus on is dihedral angles in RNA. Because like I said, we have 6 backbone angles, 1 glycosidic angle, and since we have such a low number of protons throughout RNA compared to proteins, you really need to get all the information we can if we want to get a good idea of the structure for every given RNA. And most of the, for example, the pseudo-rotation phase, or these angles beta and epsilon, and even delta or gamma, they can be just fine assessed via usual 3J coupling experiments. But especially the angles alpha and zeta here, since they are around the phosphate backbone, you cannot use 3J couplings. So here we opt to use cross-correlated relaxation rates because they're able to probe into these behaviors as well, and these dihedral angles as well. And I want to just give you a quick overview of how these experiments look like, how we can evaluate them, that they nicely work on 3 different examples. So the first example, again, because I just like it, is the pseudo-rotation phase. So again, C3 prime endo, C2 prime endo, canonical and non-canonical conformation. And in this case, we just use the 3D ACC Toxi CCH ECOSY experiment. The name is maybe more complicated than the experiment actually is. And here we extract 2D planes from a 3D experiment, and the very small 3J HH coupling is separated by this very large 1J CH coupling. And the nice thing is, if you remember the talk that Katja gave yesterday, actually the 1' position of the sugar moiety is often quite well dispersed. So if we use the 1' position as a filter for a 3D plane, we actually can get these planes quite nicely, even for larger RNAs, and we have done so many times in our lab. And the best thing, in my opinion, is that everything that is non-canonical, so everything that is actually interesting, often has a very unique chemical shift. So we have no problem with spectral overlap in these cases whatsoever. So we are actually able to probe all the important stuff using these experiments quite nicely. And the evaluation is actually also quite easy. With the 3J HH couplings, you use just K-plus parameterizations. So you simulate the couplings based on the K-plus curve for every one of those pseudo-rotation angles, and then just use whatever program you like, Excel, MATLAB, or whatever, to use the minimization function to see where would be the perfect fit for my angle, for my couplings for the given angle. As you can see here, we do not have always a perfect fit. And this can have 2 reasons. The first, obviously, is averaging. So there might be some different conformations here. So it's very thinkable that G9, there's some part that is also in C3 prime endo and not only in C2 prime endo. And another thing that we have to keep in mind is the K-plus parameterizations were optimized on very small model compounds. And while a 14-mer RNA is not very big, it's still larger than a model compound. So when you go to larger RNA sizes, you have to keep in mind that the amplitude can change quite drastically or significantly, and you have to account for this when you determine those rates with the K-plus parameterization. We can also use cross-correlated relaxation rates. These are independent of K-plus parameterizations. They are just based on this nice equation over here, and the advantage is it's linear dependent on tau c. So if we use cross-correlated relaxation rates, and the experiment is actually quite easy to evaluate because you just take the experiment where we refocus the cross-correlated relaxation rate, and in one experiment we let it evolve. And we just take the peak intensities of the reference and the cross signal, chuck it into this equation, and then we know what our CCR is. And then we can just simulate the curves again, take a minimization function and see, oh, this is not a perfect match, indicating there's again some averaging going on. We don't have completely C2 prime endo, mainly C2 prime endo, but not completely. So there's another conformation in here as well. The last experiment I will just go over very briefly are the HCP experiments. So they are using the phosphor backbone. And again, here, this is basically a combination you can think of the first and second experiment. So here we extract 3 and 2J couplings based on an intensity approach. And well, the 4D, I might have overdone it with the measurement time, so you can definitely measure it in way less time. But these experiments also quite nicely work. Again, you use the K-plus parameterization, simulate your curves, and then use a minimization function to see what the angle beta, in this case, for example, could be. I I've mentioned that that I personally really like RDCs for RNA as well. And in most cases, we just use IPAP experiments, so in-phase-antiphase experiments. I have also tried RC experiments, but in my experience, it's often a little bit quicker, or it works a little bit better with these IPAP experiments for RNA. And you have the reference sample, your line sample, you measure the HSQCs, and just, you get the dipolar coupling based on the additional splitting. So it's actually quite easy, it's quite fast. I think if you are doing structure determination, you really should think about just measuring RDCs because they give you so much information. So what does this all culminate into? We determined the structures for all three tetra loops that I started with. So CUG, GAG over here, and GCAA over here. And like I mentioned, I did a structure determination with the base pair of the loop and without. And what's a little bit worrying is that even if I restrain the base pair, the number of restraints that I measured, so the total number, somehow still led to an orientation of the C6 residue that was not in line with the normal base pair. So the orientation was, or the tilt angle was so large that this would not define actually as a C6G9 base pair. And the structure without the base pair, I think it looks fine, but it's not too interesting. So we were not very happy with these structures, although they have very low resolution. For GAG, actually, and these two RNAs were mostly worked on by David again, here RDCs look fine. We have a low RMSD. So you could think everything is great, but it doesn't describe the averaging of couplings that we have previously observed. So this doesn't actually fully explain our data. And what's even more worrying is we see quite a number of NOEs between A7 and A8, especially for the amino residues, that cannot be explained by the structure because the distance is over 7 angstrom in some cases. So while we determine our structures using ARIA had some penalties. This was still the lowest energy structure that we were able to determine. And for GCAA, actually, we have here a somewhat very usual GNRA fold. But if we look at the RDCs that for the loop, we see they're actually not that good agreement with the structure. So again, we know we have averaging. The RDCs say, we're not happy with this. And actually, David was able to see that there was a second confirmation that could be just easily restrained by changing the alpha and the zeta angles, which is actually in line with his data, to previously unseen 2+2 confirmation, where we have a stacking of A8 and G9 and G6 and A7. And this actually fits the RDC data quite nicely. So we asked the group of Kirsten Lindorf-Larsen, hey, can you help us with MD simulations? We want to figure out what is going on here. And Kirsten, and back then it was Felix Kümmerer and Sandro Botaro, they said, yeah, sure, we can do this. We run an MD simulation. We use 20 seed structures from all over the PDB. We run we run every structure for 110 frames. Then we extract the back-calculated NOE, 3J couplings, RDCs, and cross-correlation rates. We compare the average of the MD simulation to the experimental data. We also back-calculate all those values from the NMR-derived structures, compare those as well, and then we get a nice plot like this. So first, we have the MD data, always up top as a bar because we have 20,100 frames and making 20,100 dots might be a little bit overdoing it. And then we have these bundles over here. For example, this is GCAA, so the 2+2 motif and the 1+3 motif. And we see, yeah, compared to, for example, programs like FARFAR that we've also compared our data to, they're in most cases much better. But that's still not really that great in describing our experimental data. The MD simulation already does a better job. 2
minutes.
2 minutes, okay. Yeah, I think that will be doable. So the MD simulation does a better job. We did the reweighting. we extracted a sub-ensemble of 100 frames because 100 frames is much easier to work with than 20,100 frames. The 100 frames are actually better in explaining our experimental data. And these 100 frames can then be easily analyzed. And you see the force field really likes, for example, the 3' endo conformation for this loop residue. If we reweight it, suddenly, previously there was no C2' endo conformation present. We couldn't observe it. So this actually didn't explain this data well. The reweighted data explains it well. So now we see there's a large conformation of C3' endo, a large population of C2' endo. This fits very nicely to what we actually observe using NMR. And so just one example, after the reweighting, we actually observed the space pair again quite in line with what we see with our experiment. So the population matches well. And if we use a very narrow cutoff of 0.7 angstrom for the clustering, we can actually have 3 clusters explaining around 60% of our data. If we use a cutoff of 1.1 angstrom, we can actually explain 90% of our data just using clusters. And only one cluster is actually looking like a usual CUG motif that is already found in the PDB. And all the others are somewhat new structures that have not been observed before. We can compare this to the PCA analysis for all 3 or all 4 RNAs. And for example, here you see that all the programs we use to normally simulate structures, they really like to put the RNAs in very rigid spots over here. And this can also be seen, for example, for GAAG, where all the programs just put it spot on in this spot. So if you were used to simulate a structure using one of those programs, you would think, oh, this is not very dynamic, but our data tells us, yes, they are very dynamic indeed. And with that, I want to conclude my talk. I want to say thank my PI, Harald Schwalbe, and especially David, and also the group of Kristen and of Larsen, who helped us immensely with this project. And thank you very much for your attention.